Thanks, everyone. Thank you, FAIRmat, for the opportunity to talk about this work. Thanks also to the audience who sit through this bit of a painful hybrid setting. I'm really sorry, but I had to teach yesterday and tomorrow, so it's difficult to travel. So I'll talk about this work, which was done together with Louis Felter, who's a PhD student in my group, and Joe Rudzinski, who's been extremely helpful in sort of trying to exploit a lot of the features of NOMAD for this project. I would also like to thank a lot of the people on the Discord server that have been very helpful in sort of debugging and helping us out and trying out some of these features and implementing them and getting them to work. Yes, I want to talk about computational workflows for molecular dynamic simulations, and in particular coarse-grained simulations. And so this is a workflow library called Martignac, and you'll see why that is. It's because of a combination of two words that I'm going to get to in a second. And so molecular dynamics compared to, say, quantum chemistry is sort of lagging behind in terms of sharing practices. A lot of people are complaining about what the state of the art is. There's a lot of articles, white papers, as you can see here on the screen, with many authors who complain together that the sharing practices are not particularly good, and that means that their simulations are not shared or not enough. They're not easily reproducible, and that has to do with traceability. And there's also a lack of history of provenance, meaning we don't know where these simulations come from, what the input files are, what the history of these input files may be. And so this is definitely way behind compared to what quantum chemistry has achieved in the last 10 years or so. And big thanks to consortia like and efforts like NOMAD, for instance. And so it doesn't mean that nothing exists. There are some community efforts that have been brought forward to try to improve sharing practices for molecular dynamics. There is this example called BioBB, which, as I understand, is sort of a set of Python wrappers to try to connect together different molecular dynamic software codes that have been worked out before. That leads to a code that I believe is fair. So the code is sort of developed under the FAIR principles, but the data that's generated from it is not necessarily fair. There's been efforts in sort of trying to store and share data for COVID-19 drug discovery. That was done by Molsey. And this paper has been very interested in trying to sort of really try to scrape through databases like Zenodo and Figshare, and trying to find out databases that contain molecular dynamics trajectories, and then try to sort of basically scrape every information that they could find to try to gather a bit of metadata, to get some statistics, and then to try to get access to these different simulations in a more central way. And so we've been working with coarse-grained simulations. So coarse-grained means that we remove degrees of freedom, so we don't have an atomistic resolution. So these are classical models. We have classical equations of motion, but we don't even integrate all the atoms. We integrate sort of a fewer super particles. Think of these as functional groups. And we do this because these simulations are faster. There are a class of models that allow us to sort of target more biomolecular systems. Here, this is a so-called Martini model, which is a force field. So it's a model that allows us to build libraries of biomolecules. Here you can see examples for phospholipids, small proteins, and here solvents and amino acids. And we use them to try to get information about the chemical space of small molecules and their thermodynamic properties. Think of this as sort of exercises to do molecular discovery. And so we typically work with sort of large numbers of molecules and then pipe them through some biomolecular system of interest, like drugs in the membrane. And then we try to compute these thermodynamic properties and then build a low-dimensional representation of this thermodynamic property as a function of our chemical space. And so that means that we're working at high throughput. We have we have many simulations for many compounds. And so one of the requirements is that everything has to be extremely systematic. All simulations have to be completely identical. And so that calls for methods that of computational workflows to try to make things a lot more systematic than they've been in the past. And so that sort of gives the motivation to try to build these and implement these computational workflows in the context of these coarse-grained simulations. And so as a backend, we're working with a library called Martignac, which is a computational workflow manager or library. And so this workflow manager is sort of implement scientific workflows as a directed acyclic graph, where you can think of a graph, and there are nodes which are computational operations. This could be a molecular dynamic simulation. It could be creating an input. It could be calculating some observable. And then you have edges, because there's going to be some requirements. You have to run the simulation before you can compute some analysis, for instance. And that leads to this directed acyclic graph. This is something that's not new. There's been a number of efforts that have gone in this direction. For instance, AIDA, if that rings a bell, in the context of quantum chemistry, was one of the first ones to implement these ideas of acyclic graphs to get a provenance of the different calculations. And so this is what we're going to use in terms of sort of how this works with in terms of an implementation. You have to this thinks about jobs, which are sort of our unit calculations. So different compounds we're going to screen. And so we're going to have a script that will initialize different jobs, so different compounds will screen. And then we'll have another code here, which will assign the different operations. And so we'll have a Python class, and then we'll have different functions. These will contain the different computational operations of our graph. And then we will use decorators here to assign these as different elements of our graph, and then sort of specify the different edges and nodes for this graph. And so that defines the computational workflow. And one thing we'll do is that we're going to have it communicate with NOMAD. And the communication will be completely programmatic, in that it's going to be purely through the API. And so the workflow manager will try to fetch every information it can from NOMAD. And if it's not available, it will run it locally, and then it will push it to NOMAD automatically. That's the idea. And so to do this, there's this type of acyclic graph, this directed graph that we built, is done in the following way. So we first do a bit of we skip a few files that we find redundant, that we don't want to have, because maybe we would have them in every single entry, and so that's bloating a bit the storage unnecessarily. We then try to fetch the specific entry from NOMAD to see if it exists, and if it exists, we just download it and we're done. We don't have to do anything else. We just downloaded it. We have all the archive. If there is no such entry on NOMAD, then we go to the application-specific subgraph. And so I'll get to what this application-specific subgraph means, but this is going to depend really on what type of simulation we're trying to do. And so this will go into more of the application part. So this will have all the molecular dynamic simulations, for instance. And then once we're done with our our application-specific part of the workflow, then we will build a NOMAD workflow. That's a YAML file that many of you probably know about. And this dictates how these different the different elements that are in the archive have to talk to each other, and specify the hierarchy of all these files so that NOMAD understands them. And then we upload the archive to NOMAD. And this is done. This is sort of an example as to how every workflow job runs on this workflow library. And so I'll describe a bit some of these parts, and then in the very end, some of the results. So I mentioned we try to download some of these entries from NOMAD. That means we need to know exactly whether they exist, and so we need to have a unique identifier. And so the way we find unique identifiers is that we populate the comment in the upload with a JSON formatted string that contains information that's specific to Martignac. And so, for instance, it has the workflow name, the state point, meaning what type of solvent we work with, what type of lipid we work with, etc. and then hash strings for all the input files. So that we're sure that we have exactly the system and the input that we care about. And if we have a match, then we'll just download the archive. So that allows us to add custom metadata to NOMAD in a way that's relatively easy. It doesn't really allow for query, but that's a different story. These are the application-specific workflows. So that's the subgraph that's really dependent on the type of simulations we want to run. You can see again there are some arrows, and so these are different graphs again. So for instance, if we want to generate a solute, so this is just maybe a small molecule, we would first build it. That we would build a molecule, and then we would run an MD simulation. There would be an energy minimization steps, and then we run a molecular dynamics equilibration simulation. And you can see that one goes after the other. There's another example. If you want to generate a solvent, same thing. And then in the end, you have your system that's built. There are a couple points that are interesting here. One is that you can see here that when I want to generate a small molecule in a solvent, so that's a solute in a solvent, I'm actually embedding I'm using the composability of the different workflows, because I'm first going to generate the solute, which is this red workflow, and then separately I will generate the solvent, which is this yellow workflow, and then I combine them in this operation I call solvate. And so that means that I'm not going to repeat or copy this solute generation. It is a workflow that exists, and I'll illustrate this, but we don't want to sort of copy unnecessarily sort of parts of workflow, so we want to use this composability. And another aspect is that some of the calculations we run depend on multiple state points. For instance, if we run free energy calculations and we need to compute certain properties for different values of a variable, and so we'll have to run these as individual jobs. But then in the end, to compute the free energy, so the thermodynamic property, then we have to aggregate them. And this is done through an aggregation operation. This is sort of a technical aspect of working with workflow managers. Right, and so this provides us a way to generate a variety of systems, solutes, solvents, lipid bilayers, and also compute free energies for solute in the solvents, and then a drug in the lipid membrane. And so this directed graph that Martignac generates can be directly translated to NOMAD. So I mentioned this before. We do this by sort of keeping track, so bookkeeping the graph operations that are from the computational workflow Python class. We keep track of all the operations, which would be nodes on our graph. And then we use the network X library to basically translate this into this NOMAD YAML file that then NOMAD can understand. And so that programmatically we can translate what the Martignac workflow manager understands as a workflow to what NOMAD understands is as a hierarchy of simulations and entries. This composability is something that I alluded to. You can show directly as to how this is exploited. And so, for instance, if I want to generate the solute in solvent, I can look at the YAML file that's been generated, and you can see that the inputs here, if you've ever looked at a YAML file, you'll know there's a section for inputs. One starts from the users to generate solute, which is this red workflow, and you can see it's a particular upload. And for the generating solvent, which is this yellow workflow, it's another upload on NOMAD. And you can see it's really making use of independent workflows that have already been uploaded to NOMAD. And then afterwards, this purple workflow, which as you can see relies on the red, the yellow, and the blue workflows, also here relies on this new workflow, that's NOMAD entry, which is this blue one, which itself calls those ones. And so there's composability here at work, which is extremely useful when we do things at high throughput, and we really need things to be to not copy and really exploit as much as possible the information that exists. And last thing I want to show is reproducibility, or the next to last thing. We took some older papers that we found in the literature, and then we tried to reproduce free energy calculations. And so here, for instance, in dashed and solid lines, these are our work versus the reference we found in these older papers. You can see here we can we had enough information that we could reproduce as well as we could the overall protocol that was written by hand in the paper, and the fringy calculations look quite okay. If you look on the right here, there was a fringy calculation that's in this red color here, and there was not enough information to know what exactly they did. And so that means that we had to try to guess what might have gone into the input of the simulations. And we tried several of them, and these are in blue and green, and you can see that none of them fit, and so we cannot actually reproduce their simulation. And that has to do with, that sort of illustrates this problem of reproducibility, that there is not enough information, even in the text description, to reconstruct the simulations. And the last thing I want to show is actually how these thermodynamic properties can be live fetched from the NOMAD archive, which is something that's extremely appealing, I think. And so one thing we can do is sort of build little web apps that then query directly NOMAD to fetch, the content of the database. And so, for instance, I'll show you here if I can get access to my cursor. Yes, so I'll show you this. So this is maybe I can. This is a web app that I wrote. So that's called Martignac here, and it's a Streamlit app. And so this is directly querying NOMAD. Oops, this is bugging. Let me refresh this. This is querying NOMAD here, as you can see, and it's trying to find all the different databases that have information of simulations according to Martignac. And so we'll query the different databases and different entries that it can find. And you can see here it finds 2 data sets and then 745 entries. I can click on one of these application-specific workflows, and you can see this is a picture of the graph that corresponds to what Martignac understands. So this is also sort of generated. It again queries NOMAD. It takes a second, and then what you can see here is that it's going to show a list of all the different entries that correspond to this particular sort of biomolecular application. What you can see here, that is a description of the different solutes involved, the lipids, and these are the PMFs, so these are the free energy profiles. And you can see that these are live fetched from the database. They're not stored on the website. And these are directly the fringy calculations, so we can directly have a look at the fringy calculations that we get from the NOMAD archive, and then extract through the NumPy array and then show it here. And this is something that's really nice, and that allows us to sort of discover more of the content of what NOMAD offers in a more sort of specific way, which I think is something that the NOMAD GUI apps does, but sort of on a different platform. Okay, so this is all I wanted to share. So we built a computational workflow management for coarse-grained simulations. There's a few, so this is great for high throughput screening. We really like this. There's an extension to more complex systems workflows that's relatively straightforward. And this automatic download and upload from and to NOMAD is really useful because it avoids redundant calculations, and it allows us to systematically enrich this corpus of simulations available. Thank you very much for your time.